Hello everyone and welcome back. Today we have 1743, restore the array from adjacent pairs. It says here that there is an integer array nums that consists of n unique elements, but you have forgotten it. However, you do remember every pair of adjacent elements in nums. And we are given a 2D integer array adjacent pairs of size n minus 1, where each pair represents two nodes, and it indicates that the elements, both nodes are adjacent in nums. So they're connected to each other, and it is guaranteed that every adjacent pair in elements will exist in adjacent pairs, either as one connected to its right neighbor or one connected to its left neighbor. And the pairs can appear in any order, meaning that if we have connections like so, we can either return going from one end to the other, or if we start from -3 instead of -2, we can go in reversed order and return in reversed order. So I have the second example here, and I thought we could go through with it, a dry run through. There are basically 3 steps. One is identifying all the connections in order to kind of visualize our graph. The second is to find either end as our root from which we can go to the other end to find all the connections in between. And then finally, for the actual iteration, we are going to keep track of a previous node, and that's mainly to make sure that we don't ever go backwards. Whether we're starting at -2 and going rightwards, or starting from -3 and going leftwards, we don't ever want to backtrack. So let's proceed. So let's have our graph to start. And if we iterate each pair, we see that 4 and 2 are connected. So if 4 is connected to 2, then 2 is also connected to 4. And for the pair 1 and 4, 1 is connected to 4, which means 4 is connected to 1. And let's make sure that these are appropriate. Okay, and -3 is connected to 1, and that means 1 is also connected to -3. And this adjacency list actually helps us to visualize what this actually ends up looking like. We can draw that out here by going through each node. So let's start from 4. 4 is over here, and it has connections -2 and 1. So let's say that -2 is to one side and 1 is to the other side. So these are currently connected, okay? And then -2 is connected to 4, already represented here, and 1 is connected to 4 and -3. 4 is already here, so let's just add the -3. Oops. Okay, and then -3 is connected to 1. If you notice, the 2 nested nodes always have 2 connections, left and right. Whereas the 2 edge nodes always have exactly 1 connection going this way, 1 going the other way. So we have our adjacency graph, which helps us visualize, adjacency list, which helps us visualize our graph. And just by going through the length of the connections, we can determine if that node is an edge node. Once we have that, we can actually already start building our result. Now we've already identified one edge node, which contains our first number. So let's say that we're going from the left to the right. We have -2, okay? And then we can set 2 pointers, one pointing to previous. For previous, let's use a P, and one pointing to current. Previous starts as null, and current can start at one of the edges. Once we have 2 pointers, we can actually traverse the connections of the current node. Current node has 4, and 4 is not a previous node. We're not going backwards, so we can add that to our result. So now we have a 4, and once we have that, we can move along our 2 pointers, where current is now previous, and the connection that we just added is now our current. Okay, so this is done. And 4 has these 2 connections, -2 and 1. However, -2 is a previous node. We don't want to go backwards, we want to go forwards. So let's ignore that one. And 1 is not going backwards, so we can indeed add 1 to our result, along with moving both our pointers forward. So now our previous is where current was previously, and our current is the new connection we just added. And we've already exhausted this. And if we traverse the connections to 1, we see that 4 is going backwards, so we don't want to do that. Going forwards, we have a -3, which we can add to our result. And then we would have exhausted 1's connections. Once we're at -3, we can move these 2 pointers here. And then once we're at -3, we can't go back to 1 because that would be going backwards. So we're essentially done. And this can be translated to code quite easily. So I have it already written out, but I'm happy to go over. So we first create a graph where each pair is added to the other side. So we have bidirectional connections. We initialize the root to none and then traverse each node and its connections in the graph. And if we find connections, which is exactly the size of 1, so if we have a node where its connections is exactly 1, it means that one side is empty and only the other side is filled. So for -2, one side is empty, only it can go one direction. Then we can set root to that node and break out. Okay, steps 1 and 2 are done. Now for the traversing part. We initialize result to our first identified number, the root, and then have 2 pointers. Cur to point to the node that we're currently iterating, previous to point to the node that we iterated last, which of course is none to start for our edge node. And while the length of our result is less than the total number of nums that we want to return, we can go through each connection in that graph of the current node. So each connection, meaning for this node, every connection in its connections list. For this node, every connection in the connections list. And as long as that connection does not point backwards, as long as we're not going backwards, we can add that connection to our result and move both pointers along and break out of that iteration. And at the end, we should have a result containing all of our numbers going from one direction to the other edge. Let's submit that. And as you can see here, it is also pretty efficient in memory and runtime. Once again, that was 1743, restore the array from adjacent pairs. Thank you so much. Happy coding, and see you next time.